Let's begin by reminding ourselves how autoencoders work. So the idea of an autoencoder is that you can take a data sample, so one of the original training data items X, you pass it through this trainable encoding to compress it to some low dimensional encoding that we call a latent representation Z. And then we have a trainable decoder that tries to reconstruct or approximate the original input X. And we train the encoder and decoder together to minimize the reconstruction error between X and X prime. And the hope in doing that is that we learn this compressed latent representation that might be useful for other things. However, the autoencoder doesn't actually care how that latent space is organized. So long as it manages to compress the data, that's fine. So the goal is to just get the reconstruction error as low as possible, and the latent space can be used in whatever way the autoencoder likes. So in other words, it's free to overfit to the training data if it wants to. Now this brings a problem if we would want to generate new instances, because there's no guarantee that the regions of the latent space in between our training samples is going to be meaningful in any way. On top of that, we don't know anything about how the points within this latent space are distributed, so we would have no reasonable way to sample new points from the latent representation to put through the decoder and get realistic output. So in general, what we would like is a well-organized latent space, and let's just talk about what we mean by that. So imagine that we have some set of shapes, and we would like to learn a low-dimensional representation of these shapes. So here I've shown 4 different shapes, and imagine that I'm embedding them into a 2D latent space, and let's say I train my autoencoder and they embed like this. So the problem with this is that dissimilar shapes have ended up close together in the latent space. And the problem with that is that if I try to interpolate or sample new positions, maybe for example between the embedding of the square and the triangle, I might expect to get a shape that's something like an average between a square and a triangle. But actually, I've got no guarantee that this will in any way lead to a sensible shape. On the other hand, a well-organized latent space would have this nice property that points that are close together in the latent space decode to similar shapes. So here, the square and the square with rounded corners are embedded to similar positions in the latent space. And this gives me some kind of smoothness and some guarantee that when I interpolate between my training samples, I'm going to get sensible output. So variational autoencoders are one way of ensuring this sensible layout of my latent space. So let's go straight into how they work. So the key difference is that our data sample X passes through the variational encoder, but this time it doesn't directly go to a latent code. Instead, it goes to a latent distribution. Now this sounds a bit weird, but what we're saying is for a given X, so conditioned on X, there's a whole distribution of possible Zs. We'll make that concrete in a minute, how we might actually realize this. But let's say we've got this distribution, then we can sample from it a Z. So we had this conditional distribution of how Z will be distributed given that we observed X, and now we can draw from that distribution a specific Z. So now this is exactly as before, it's a latent representation sampled from this latent distribution. And the decoder is as it was before, so that just takes a latent representation, a latent vector, and decodes back to the original data space. And part of this is that we hope that the decoded value X prime will be close to X. But the complicated bit is this encoding to a latent distribution. So what we normally do is assume that that distribution is a normal distribution. And that means all we need to describe it is a mean and a variance. So the variational encoder E all it needs to do, instead of directly outputting Z, it just can output the mean and variance of a normal distribution. We can then sample Z from that normal distribution with given mean and variance, put Z into our decoder, that gives us X prime, and our reconstruction loss can be as before, so some error metric between the original X and the reconstructed X prime. Okay, so that's how an autoencoder works, a variational autoencoder. Let's just think a bit about why it works like that. So why would you want to encode to a distribution? Well, there's a few different reasons. First, it captures the ambiguity inherent in real-world data. So remember, all data is noisy, and we should probably capture that uncertainty when we encode it. So instead of saying, my observed image maps to just this single point, I'm mapping it to a kind of blurry region captured by this distribution, representing the fact that that image itself might be a little bit uncertain. The second thing is that by encoding to a distribution, we will ensure a smooth latent space, because different samples from the distribution have to decode to similar output. So if my, for example, image encodes to a distribution and then I sample from it and decode, all those different samples should ideally give me something similar so that they're close to the original input image. Okay, so we've got this concept that we're going to encode to a distribution. Is that in itself enough to ensure that we get this desirable, well-organized latent space? Well, unfortunately not. We can still easily overfit with such a model. All the model needs to do is encode to a very low variance, approaching 0. That reduces each data sample to a point. So essentially, the mean just becomes what we had as Z before. So we just encode each data sample to a mean, and then it's just reduced to an autoencoder. There's no variance around this mean. So to ensure a well-organized regular latent space, we need to introduce some additional regularization. So the example I gave here of overfitting is sort of visualized by this diagram. So we have 3 shapes encoding to a distribution, but they're very narrow, the variance is low, and that means that there's space in between these distributions which the decoder would never get to see. So this would lead to an undesirable latent space. With appropriate regularization, we'll have a latent space that's smooth everywhere. So we have a well-defined decoding, and as we move around, we should gradually transition from the edge, for example, of the triangle distribution into the edge of the square distribution. So we'll reach a region that's sort of a low probability triangle and a low probability square, and then we can move between those two parts of the space. So this would be a desirable latent space. So how do we actually achieve that? Well, what we do is we encourage the encoded distribution to be close to a standard normal distribution. In other words, with 0 mean and variance 1. So we do this by measuring the Kullback-Leibler divergence between the distributions. This is just a particular notion of distance between probability distributions. So we try to encourage that the distribution that we encode to, that depends on our encoded mean and variance, stays close to a standard normal distribution with mean 0 and variance 1. Now, in the special case where it's a multivariate normal distribution and we're comparing it against a standard normal distribution, this has a very simple form that's easy to implement. So it just depends on the values in the mean vector and the values in the variance vector combined according to this formula. And this gives us a measure of the KL divergence between these two things. So we can use this as a loss, and in order to train our variational autoencoder, all we do is minimize the reconstruction loss as we did for an autoencoder, but also this KL divergence loss, which is going to try to push the distributions for all the data samples towards a standard normal distribution. So one final detail, how do we actually sample from the encoded normal distribution? Well, we could do it by sampling directly from the encoded distribution, but in practice what we do is something called the reparameterization trick. So first we sample epsilon, some noise from a standard normal distribution, and then we scale and shift the standard normal distribution to the encoded one. So in other words, all we have to do is scale epsilon by these standard deviations. This is just element-wise multiplication between these two vectors, and add on the mean. And that gives us our z, drawn from this original distribution but via the standard normal distribution. So why do we do this? Well, here's the diagram from the original presentation of this method. And the idea is this. So if we try to draw our z directly from the distribution that we get from the mean and variance, we would be trying to back propagate through something that is itself random. However, if we reparameterize, so now we've got epsilon as this source of noise, and we're just adding on the mean and we're scaling by the variance to give us z, then we can see in the computational graph, we don't have this problem of trying to back propagate through any node that is itself a random process. So epsilon is just a source of noise, but it doesn't depend on anything, so we don't need to back propagate through that into anything else. Whereas the mean and variance that are coming out of the encoder network, those are now just values that are getting added and multiplied, and it's not a problem to back propagate through them. So if this all sounds a bit complicated and strange, I wanted to show an implementation to show really how straightforward this is. So here's a sort of sketch of implementing a variational autoencoder in PyTorch. So you would initialize it by giving it whatever your encoder and decoder models are. And then we've got this reparameterization implemented, which simply takes a mean and a standard deviation. It generates this random epsilon just using a standard normal distribution. And then it creates the sample from this latent distribution as we just saw. So multiplying the epsilon by the standard deviation and adding on the mean. So that gives us the latent vector. So now in order to actually pass something through this variational autoencoder, we input an X, a data sample, we encode it. The encoder must return the mean, and the way we actually represent it is the log variance. Since variance has to be positive, we allow it to predict any value, which could be negative, and we treat that as the log variance. If we then take the exponential of it, it's guaranteed to be positive. So this encoder could be anything. It could be a CNN, it could be an MLP. Just at the end, it probably will have, say, two linear layers that predict the mean and the log variance separately. So it's kind of got two outputs from this network. We then pass those to the reparameterization function. So we give it the mean and the standard deviation compute from the log variance. So that's all we're doing here, converting log variance into standard deviation. We've now got our latent vector, which we can put into the decoder, and that gives us the predicted output, the x prime from before. So we would return this reconstructed sample. We could use that to get our reconstruction error, but we also want to return the mean and the log variance so that we can also compute the KL divergence loss. So let's finally just see how this actually looks in practice. So this is a visualization of 2 dimensions of the latent space when trained to autoencode the MNIST digits. So on the left, we can see a visualization of a conventional autoencoder. The color of the points corresponds to the particular digit. And we can see that the latent space is organized in a somewhat strange way. So for example, there are very sparsely sampled regions where there's nothing lies. We can see that there would be no obvious way to draw random samples from this. It's not exactly uniformly distributed, it's certainly not Gaussian distributed, and that's because there was nothing to encourage the autoencoder to do that. And we can see strange things like the 2s here, the blue points, are kind of split into actually 2 regions, or possibly even 3 over here. Yeah, this is also 2s. So that's strange. We would expect the same digit to encode to the same region of the latent space. It means that a large movement here will hardly change the output. On the other hand, a small movement over here will completely change from a 2 to, I guess this is a 4. So on the right, we can see the equivalent plot, but now with a variational autoencoder, and we can see that the points now encode to distributions, which are shown by these soft plots. And we can see we've got a much better organization now. So we can smoothly move between almost any points, and the latent space is still well covered by the training samples. There's also some kind of sensible organization, so the same digit always encode to similar regions of the latent space. There's also some logic to the organization. So for example, out on the side here, the purples, they're all 1s. The thing next to them, the oranges, are 7s, and the 7s also have a vertical line, so that kind of makes intuitive sense. Over on the left, the blacks, those are the 0s, so again they're somehow different to everything else, but the closest thing to the 0s is the yellows, which are 6s, and they both share having a large circle in their shape. So you can see we've ended up with a much better organized latent space.